At this point, you've learned about 4 of the 5 types of chemical reactions. You know what synthesis and decomposition are, the reactions that build more complicated molecules or break them down to make them simpler. And you know what single and double replacement are, the ones where atoms switch places within compounds in chemical reactions. Today you're going to learn about the last type of chemical reaction equation, which is indispensable in real life. We use this all the time for transportation and making electricity, and that is the combustion reaction. Today we're going to be learning about this last type of chemical reaction. First of all, let's define what combustion is. Combustion occurs when a substance called a fuel combines rapidly with oxygen and maybe 1 or 2 other things to produce waste products, exhaust. And those exhaust products are usually all oxidized. So they have an oxygen atom somewhere in them. This chemical reaction equation is a prime example of a combustion reaction. This is the burning of octane. Oftentimes, combustion reactions occur with hydrocarbons as one of the reactants. A hydrocarbon is simply a molecule made up of only hydrogen and carbon. So you see there's a hydrocarbon plus oxygen, and then all of the waste products in this reaction, carbon dioxide and H2O, have an oxygen atom in them. They are oxidized products. Okay, let's take a look at how this reaction plays out. First of all, we have our C8H18 octane molecule. This is the molecule that's usually present in large numbers in gasoline. And then we need oxygen to combine with octane to make this reaction happen. So here's how we're going to start this reaction out. Let's break apart the octane molecule and the oxygen molecule, and you're going to realize right away we are missing a lot of oxygen molecules. We need to make everything on the product side of this either H2O or CO2, but I only had 2 oxygen atoms to start with. So I'm going to make a whole bunch more oxygen molecules other than just the one that we started with. Let's add all of these. We have a total of 13 oxygen molecules here on the left-hand side, and those 13 oxygen molecules should give me enough to change everything on the other side to either carbon dioxide or water. All right, so let's take a look at how this next part of the reaction plays out. I'm going to move all of these oxygens that haven't been moved over yet to the other side. Ooh, I've made all carbon dioxides and waters, but do you notice how in the bottom left corner, I've still got 1 oxygen that won't combine with anything because it doesn't have any additional carbons or hydrogens to combine with. And I can't just leave it as a single oxygen all by itself because that's not part of the chemical equation. So I need some more things to connect to that oxygen. I either need more hydrogens or more carbons. And the only way I can get more hydrogens and carbons is to add another C8H18 over on the left to all of the other stuff that I have so far. So here's my next hydrocarbon octane molecule. That's going to break apart and move over to the other side. And now I've changed that lone oxygen to water, but now I have a whole bunch of carbons and hydrogens that are once again unbalanced. So I'm going to put my octane molecule back on the left-hand side where it belongs, and I'm going to need to create some more oxygen to make this work. Here I've added 12 more oxygen molecules. Each of them are going to bond either 2 of them to a single carbon to make carbon dioxide, or 1 of them to 2 hydrogens to make water. Let's move them over. And now I have completely changed all of the reactants, carbon dioxide or water. So let's take all of these oxygen molecules and put them back over on the left-hand side as well to show how many we had. And you'll notice as you look at this reaction that this is a cluttered mess because combustion reactions usually have pretty big coefficients unless you're dealing with really small fuel particles. C8H18 octane is a huge fuel molecule with a lot of energy in it. That's why we use it to propel vehicles forward. Now, we have 2 fuel molecules of octane. we have 25 whopping oxygen molecules. That's a huge amount of oxygen. We have a total of 16 carbon dioxide molecules as waste products, and a total of 18 water molecules as waste products. Now, just think about a vehicle for a moment. In order to make a car run well, you need, first of all, a really well-developed air intake system that can pull in a huge amount of oxygen. You need 25 oxygen molecules just to burn 2 molecules of gasoline. And then you also must have a very good exhaust system to get rid of all of the waste products that are developed. When you add together 16 and 18, that's 34 molecules of waste products that you need to take away from the engine. That's why cars have such well-developed exhaust systems. The 18 water molecules, by the way, are the reason why on a cold day or on a damp day outside, you see water vapor coming from the exhaust pipes of cars. And the 25 oxygens that are required mean that this is a very oxygen-intensive reaction. But most combustion reactions are oxygen-intensive. And here's the deal. The air that you're breathing right now isn't made up of 100% oxygen. There's a lot of other stuff in the air that gets in the oxygen's way. The air is actually mostly nitrogen. There's also things like water vapor and carbon dioxide already in the air. So because air isn't pure oxygen, these reactions never really happen in such a way that all of the reactants, all of the fuel, gets burned with oxygen to produce very pure products. Instead of getting just carbon dioxide and water vapor, oftentimes we get what's shown in this chemical reaction. This chemical reaction shows the burning of propane gas, that's C3H8, that's our fuel. Notice it's combining with oxygen to form carbon dioxide and water. Those are two typical waste products of a combustion reaction. But we also get carbon monoxide because there's not enough oxygen to make pure carbon dioxide. And also, we're going to have some sooty, plain old carbon atoms left over. This is what soot is. It's atoms of carbon that were unburned. We're going to have some of those left over at the end as well. Let's watch and see how this reaction takes place. Now, here's my propane and oxygen, and those are going to react and form carbon dioxide, water, carbon monoxide, and just plain carbon. Now, you'll notice, again, because I only had one oxygen molecule to start, I am missing a bunch of stuff. So let's just put back on the reactant side what I started with, and I'm going to need a lot more oxygen. Here I'm going to make 3 more oxygen molecules. But did you notice that even with 3 more oxygen molecules, I still have one left over that has nothing to bond to? Now maybe you're thinking, why doesn't it bond to that carbon to make carbon monoxide? But you have to have at least one molecule of each of your products for this to be a valid reaction equation. So there has to be at least one carbon that's all by its lonesome. Here I'm going to take this oxygen and just move it over for now, knowing that I need something else to bond with it. To make either carbon or hydrogen to bond with that oxygen, I have to make another C3H8. So here I'm going to put the oxygens back. So I have all 4 of the oxygen molecules that I used here. I'm going to make another propane, and we're going to move that over to the other side. And we're going to bond one of them to that free oxygen to make carbon monoxide. But now I have a whole bunch of other things that aren't connected yet, so we need more oxygen to make this work. Here's my propane molecule that I need to put on both sides. And I'm going to add yet 2 more oxygen molecules, and those are going to break apart and fill in all the spaces that they need to. Okay, so let's just count up. 2 propane molecules plus 6 oxygen. Notice you need a lot of oxygen to make these reactions work. That's why combustion is often called a rapid reaction of oxygen with other things, because it takes a lot of oxygen for a lot of these chemical reactions to drive forward. We only have 1 carbon dioxide, so that's just going to have no coefficient at all. We have a total of 8 water molecules, 2 carbon monoxides, and 3 individual carbon atoms. That's how this reaction with a deficient amount of oxygen, so we couldn't perfectly just make carbon dioxide and water. That's how this reaction took place. All right, so this is another combustion reaction. Let's take a look at some more examples of combustion reactions. Combustion is just the rapid combination of oxygen with another substance to make an oxidated product. So here, lithium is combining with oxygen. Lithium is our fuel, and we're making lithium oxide in the end. That is also combustion. Now let's just compare this to the reaction up above. The reaction above was one of those typical hydrocarbon ones, where we had propane and oxygen combining. Notice that in that reaction, there was an individual carbon all by itself. Sometimes that will happen with hydrocarbons, and carbon can be all by itself without an oxygen attached. But you're going to see that in all of these other combustion reactions, the products all have oxygen in them. Carbon is one that's allowed not to sometimes as you produce soot from burning. Let's take a look at another example of a reaction. In this case, we have zinc sulfide combining with oxygen rapidly to make zinc oxide and sulfur dioxide. And in this last one, we have a substance called propanol that's almost a hydrocarbon, except it has one oxygen atom in it, combining with oxygen rapidly, 9 oxygen molecules to produce carbon dioxide and water. Again, just like a typical combustion, which forms carbon dioxide and water, oxidated products that have oxygen in them. So these are combustion reactions. Again, a combustion reaction is when a fuel combines with oxygen, and maybe some other reactants as well, to produce oxidated products. Products that have oxygen atoms somewhere in them. And again, the only real exception to this is sometimes you'll have free carbon soot that forms when you burn something incompletely. Now you know all 5 types of chemical reactions.